I think in our future design, especially the system level design, data flow architecture is mostly used, and that's the main advantage of FPGA design. Okay, data flow means you can have a optimized data path, and which is not available with a hardware device like a CPU or GPU. Yeah. So FPGA design, we should maximally use the data flow scheme. Yeah, and using the data flow, they have a very restricted rules, and of course, they always have a way to get around it. And I see many design, uh, we can accommodate most of the design we see. Yeah. Okay. Okay, let's see the characteristic of a data flow. Okay, so basically you have a sequence of a task run concurrently. And the key is the sequence of a task runs without waiting for the previous task to complete. Yeah, and the start of the task solely depend on the availability of data coming from the previous task. Yeah. And normally the sequence of a task communicate by a channel, and the channel structure can be FIFO or memory. Okay, so this one give you a clear idea. So you have a function and sequence of functions. Okay, when you call the HLS with pragma, what it does is it creates a channel between the functions or the task. And the channel include two parts. One is the for the data FIFO, for the data transfer. And for the data buffer, it could be the FIFO or ping pong buffer. Okay, it got to be a ping pong buffer. Otherwise, these two cannot be parallel. Okay, if you have a only single buffer, then this thing has to write to fill this buffer, and next one start. And before the next one starts, the previous one cannot start. Okay, so you have to use the ping pong. Ping pong means you write to this one, and then the next one can start reading from this block. And then you start the previous uh, function can start working and write the output to next buffer. So you need ping pong buffers. Okay. And it does not limit to a chain of a process. As long as it's a DAG means directed, okay, acyclic graph. Okay, directed means it's coming from a directed means that's from a producer and one consumer. One producer data and one consume the data. That's directed. Acyclic, that means there's no feedback loop. No feedback loop. Okay, so any DAG structure can implement with the data flow. Okay, and actually, however, the feedback happen all the time in our design. For example, like the processor pipeline, it has a feedback. Okay, like the data forwarding. Okay, so that's a kind of feedback. So actually, for data flow, you can still handle the feedback. However, need to be very cautious to prevent the deadlock. Okay, and deadlock, you can overcome the deadlock by appropriately manage the data FIFO. Okay, make sure it doesn't create a deadlock. Yeah. However, with the feedback path, the feedback easily occur. the deadlock easily occur. Yeah, but there's a way to overcome it. But you need a lot of inside knowledge about how to handle the FIFO steps. Yeah. So for data flow architecture, it is a distributed handshake architecture versus the pipeline. That's a central control by finite state machine. That has already explained that. Okay, the channel, there are two types. One is FIFO and one is ping pong buffers. Okay, so for AAHLS, it creates a FIFO for scalar, okay, or pointer or reference parameters, as long as it access in sequential order. It's very important. It got to be sequential orders. So that's why when we said that when you merge two loop and the loop, if it says fivefold, then after a merge, the order may not be determined. Yeah. Then in that case, that you cannot do the merge. And normally for this case, the FIFO depth is 2. By default, okay, use depth 2. Another thing is the channel you can implement with the ping pong buffer for array, okay, and you use a 2 block of array. And it's important, the memory size is created with the maximum number of consumer or producer elements. Okay, so for example, for this function A, and this is a function B, okay, and then they communicate with array A array, okay, and so the internal ping pong buffer, the depth will be the depth of this array size, okay, so the memory depth is the A array size by default. Okay. Yeah. And this array you can also implement with FIFO, right? As long as it's a sequential access, you can specify this array. By default, for array, you create the ping pong buffers. Okay. And you can override, specify that use FIFO. Okay. If I use FIFO, then the FIFO depth by default will be the A array size. Okay. So if you know the throughput of these two functions actually the same, the throughput rate is the same. That means when you produce one piece of data and this guy can consume it right away, the throughput rate is the same. Okay, then you can reduce the FIFO size. Okay. Another thing is throughput. Keep in mind, throughput is not, and the latency is quite different. These two functions could have the same throughput. For example, they can produce one data in one cycle, or take one data in one cycle. But these two functions may have a different processing latency. This latency may be different, right? So if these two latencies is different, then you have to appropriately specify the FIFO size in order to bridge the latency. Understand? For example, I will explain more in the later slide. For example, I have a function A and function B. And these two has the same throughput rate. Okay. However, this one take the latency is 5 cycle, and this one the process latency maybe 8 cycle. Okay, the data out and take a 8 cycle data, the data out. Then imagine how the FIFO depth, then you need to have an appropriate FIFO size. Yeah. Otherwise, you will overflow the data. Yeah. That, yeah. So that need to be careful. Yeah. Okay. So there are all different cases. For example, this one may come out the data going to two FIFO and fit into two functions. That's all different kind of the DAG graph. Yeah. Then yeah, you need to appropriately assign the FIFO depth. Yeah. Otherwise, sometimes you will create a deadlock. Okay, so there are basically two programma you will use for the data flow. One is the HLS data flow, or the channel you can use the stream. Okay, okay, let's talk about canonical form, the standard usage of the data flow. The data flow can be used for function or for loop. Okay, let's say when you use the function, how do you use the data flow? In this case, refer to this diagram. And as a function, you have three sub-functions, okay, like this one, the three functions, and each one using the string to connect these functions. So, wait, okay, let's look at the code here. So when you use the data flow for functions, then you create that the in is the input, okay, and then it output to the in string. So there are stream interface between the function. In string generate the out string, and the out string generate the output, okay. So in here you create two string, in string and out string, used to connect these two functions. Okay, and for string, you specify the depth. Yeah, and for this three function, you use the HLS data flow. Okay, so keep in mind that's how you use. That's the standard format to use the data flow. First, you use the HLS data flow. Okay, within this functions scope, and then the interface between this function, you create the string. You create a string. And for the string, that for example, for read input, you read the memory array and then you push it into the in string, output the string. Yeah. And you want to get the string data, okay, it provides a function read. That means read the FIFO. Okay. Of course, you can also write this way, in string write. Actually provide read and write. For write, then you put the in I. These two are equivalent. Okay. For read input, you read from external memory, and then you push to the in string. And for next function, you try to read from the in string and push to the out string. Okay, this looks very simple, right? Yeah. Okay, so that's the use of data flow in function data flow. Okay. Another way is okay, for loop. Uh, for loop. Okay, loop is a little bit more complicated. Okay, let's look at this. So there's a for loop. This for loop you can think of as a function. Okay, the function is a forever loop. Yeah. Okay, and inside you have a two loop, and this two loop you want to do the data flow. That's important. If you don't use the data flow, then you have to complete this loop. Remember, loop is executed in sequence. We see the example before, right? So you have to complete everything in this loop before you start this loop. Okay. But if you apply the data flow, then when the data produced using the this for this one the R5 yeah, and this two pipeline this two loop actually using the this memory, yeah. So the tile actually is a string, I think. Yeah. Actually, this since it create a data flow, so this is a string channel. String channel. Okay. So the R5 will write it out, and the next loop, when one data produced, this loop can read in next cycle. Okay. So this the standard way to do the data flow between the loop. Okay, that's one thing. Another thing is make sure the loop, the innermost loop, you have a pipeline. Okay, there are two things. So that's a requirement. That's how you write the data flow between the loop. Okay, first, the initial value has the index is quite important. There's a strict how to say that there's a restriction on how you specify the index. It has to start with a 0. Okay, the FIFO always yeah, it's a requirement. Yeah. So in the loop header it has to set to 0, and the loop condition has to be a constant. Okay, the second requirement, and the third one has to increment by 1. Okay. And you need to have a data flow pragma inside the loop, data flow inside this loop. Okay, this one you can put into function. You can actually specify this as a function. It's okay. Yeah. And only a single loop counter and inner loop need to be pipeline. Yeah. So those are the requirements, standard way to use the data flow inside a loop body. Yes. Oh, okay, okay. What do you mean? Oh, so this way. Oh, yes. You have a question?
Yes.
Yeah, yeah, please.
Professor Lai, I want to ask, in this case, in this code,
Um,
so it using the ping pong buffer, right?
for yes, that's the memory array. You will use a ping pong buffer. That I'm not sure. Yeah, for this one, yeah, you may use a ping pong buffer. Yeah,
Okay,
yeah.
thank you.
So if it's a ping pong buffer, it does not generate one data to output. Actually, for this restriction, since with this restriction, data can use the FIFO. If a ping pong buffer, it not necessarily is sequential access. Look at here, all the requirement here. First, it says the counter initial 0 and increment by 1. Yeah, all the requirement here It looks like you can use FIFO to implement this string. You can use string implement this array, memory array. Yeah.
But because the second loop, it needs the two-dimension information. So if we use FIFO, then how
It
can we
doesn't matter
call?
because a two-dimensional array still is a one-dimensional array because it's an
Yeah,
index calculation.
yeah,
Yeah. So when you calculate index, it's a sequential number going up,
yeah.
right? Yeah. But it's a really good question. I do encourage you. You can. I didn't really write the code to see the result, but based on my understanding, for this kind of a code, you can implement with the FIFO. You can specify, but remember, by default, if it's an array, it use a ping pong buffer. That's by default.
Mm-hmm.
Okay, so that you are right. But I think in this case, you can specify using FIFO because it meets all the FIFO requirements.
Yeah.
Yeah,
Okay.
and using FIFO is much more efficient.
Yeah.
Yeah.
Okay. Thank you.
Okay. Good. Okay, let's proceed. Yeah. Okay, let's introduce the rules for data FIFO. Okay, there's a rule for data FIFO. Those rules are pretty obvious. First is a sequence of function called forward. Okay, it says no feedback. Okay, and so for each variable, can only one read process and one write process. Okay, so it's okay. And there's the function return type. There's no return value. Okay, and also no loop or carry dependency. Yeah, very simple data flow graph. And there are certain limitations. Okay. However, for DAG, it's not for DAG. There have this all different kind of graph. For example, like there is a fan out, and often happen there is a merge case. So we can still handle this, but need to change the code a little bit. First, limitation, there's a single producer and consumer violation. And sometimes it's a bypass task. Feedback is not handled, but it can handle in other slides. PPT, yeah, I will explain the feedback. It's much more complicated because the deadlock case, there are certain cases will have a deadlock. That's explained in my textbook. Yeah, you can read that too. And conditional execution task, multiple as a condition. Yeah, let's see the example here. Okay, first is a single producer consumer, like in this example. Yeah, and this loop, the temp one, actually goes in two other loop. Okay, so it's graph like this one. Yeah, in this case, you need to restructure your code to introduce the so-called split function. What split function is, simply put into a two channel. Okay, so let's say you have a loop one, and then it goes introduce a sleep and the split. And the split create two channel, two FIFOs, and each feed to one downstream function. Okay, you use this one to fix the single producer consumer violation. Okay, the next one is a bypass task. Okay, in here, the loop one produce two outputs, and the temp two is used in the skipped one, the loop two. So when you you can see this data flow like this one. Okay, so the output temp2 skip the loop 2. So for this case, you can see that that introduced the latency, right? The temp2 create actual, because for the temp2 it doesn't have a loop 2 latency. Yeah. So in order to balance the latency or fix this constraint, you have you have the temp2 also goes to the loop 2, and loop 2 you simply bypass it, and you try to make sure the temp1 to temp3 and temp2 to temp4 has the similar latency, same latency. Otherwise, they will create, because there's a remerge. Okay, when you remerge, you must have the data available for these two channels. Otherwise, this thing cannot initiate. In this case, to do that, since there's only one cycle here, if if you use a multiplier, it takes 2 cycles, for example. Okay, in this case, you want to delay 2 cycles before you push into the temp4. So these two paths is better to have the same latency. Yeah. Otherwise, you have to adjust the FIFO depth. Yeah. You would rather to delay this. Otherwise, these two FIFO depths will be different. Yeah. Okay. When you bypass, yeah. Okay. And then the other one is conditional execution of the task. In here, okay, if a if statement to decide whether you execute this loop or execute the other loop. Okay, and that means you have a two data flow, for example. Okay, and this function, the loop 1 and the loop 2, they may can execute or not execute. They will create a problem. In this case, you want to move the if statement inside the loop. Yeah. Okay, so make sure the execution of the loop is determined instead of depend on the input variable. Yeah. Okay. In here, the loop with the multiple exit condition. Yeah. For example, in this loop 2, okay, there are 3 exit conditions. One is the loop index exit. One is the break statement. Another is the continue statement. Yeah. So remember that the break and continue statement cannot be used in loop if you want to do the data flow. Okay, so these things is not allowed. Okay, here, first, the data flow does not propagate through the hierarchy. That's important. So normally, when we write the code, we try to organize the code for readability or for structure that you have a nested function code. Okay. So in this case, for the data flow, for example, you have these two functions. Okay, and you apply data flow here. Okay, and this function, you have a sub function. This is a sub function. Okay, so the data flow does not propagate to the sub function. Okay, so in this case, that you want to, for this function, you have to use data flow again to make these things connect. Of course, you can always rewrite your code to bring this function up. you can write this one. But if you do this way, that make the code not quite readable. Yeah. So not easy to read or not logical. Yeah. So if you want to maintain the same hierarchy, make sure the data flow does not propagate to the subfunction, then you have to use the data flow in subfunction. Yeah, to make the whole thing like a data flow. Okay. Yes. Oh yeah, yeah. Speaking.
Yes. I want to ask on the page single producer consumer violation.
Okay.
In that case, can we use a merge loop to solve the problem?
Use what?
Merge loop.
Oh, merge loop.
Yeah. Can we merge loop 2 and loop 3 into a single loop?
You say this loop one, two, three.
Yeah. And
If
we
you merge, then there's no need for data flow.
I mean, only merge 2 and 3.
Oh, you mean merge what?
Loop 2 and loop 3.
Oh, loop two and loop three. Oh, yes.
Okay.
Yeah, you can do that. Yeah,
Okay. Thank you.
yeah, right. Hmm.
Yes. Okay. Thank you, Professor.
Okay, yeah, you can do that. When you merge, that's actually no split issue. Yeah, they become one loop. Right. Okay, good. Yeah. But remember, merge has the merge rules. You have to, make sure meet the merge rule. But for this example, this is a simple example. Yeah, this two loop can be merged.
Yeah.
Yeah, you're right. Good. Data flow configuration. Okay. So as we say that the data flow either FIFO or ping pong buffer. Okay. For scalar, pointer, and reference, okay, the HLS use FIFO. If it's an array, it default using a ping pong buffer. But you can still use FIFO. Make sure it meet a certain requirement, as I said in the previous slide. It has to be a sequential access. And for the top function, the interface, you can use the AP5O or the XI string or AP handshake. Handshake is like a FIFO, right? Remember, there's a valley, right? And you have a ACK, right? Right. Valley is like not empty, equivalent not empty. ACK means pop, right? So AP50, APHS actually very much like AP50. Yeah. So at the top function interface, you can use these things. And inside the function, you want to connect different sub-functions in your create stream. Yeah. Okay. Yes. Oh, Yilin. Yes. Speaking.
Okay. Hi, Professor.
Yeah.
I want to ask which caused the less area, the FIFO or the ping pong buffer?
Less area. Oh, definitely FIFO. Because few things, okay. First thing is FIFO, there's no address generation logic. Okay, that's one thing. Okay. And second, FIFO you can arbitrarily specify is the FIFO depth. Okay. And the FIFO in my FPGA slide, FIFO can be efficiently implemented with LUT, distributed RAM. It's very, very efficient. If you use a ping pong buffer, it has to use a block RAM. And for each block RAM, the minimum size is 18 kilobit. Okay, so even though you only use a few hundred bits, but you still occupy one block RAM. And most likely, you cannot merge multiple ping pong buffer into one block RAM because they all have its own. First, since they run concurrently, yeah, so you cannot share the ping pong buffer with one block RAM. It's almost impossible. So in that sense, we like to use a FIFO as much as possible. Yeah. Okay.
Okay, thank you, Professor Lai.
Right. Unfortunately, I didn't have a time to lecture the APGA, but I do encourage you to read the APGA PPT. Yeah, a lot of information is important. Okay, the stable array. Okay, so it's often you happen these things that you have a two input, and the two input fit into a different stage of the data flow. Okay, so that's the case. So for the input, normally you have a block level protocol. Okay, first you use a block level protocol to initiate to start executing this block. Later on, then there will be a data phase. You start moving the data and execute each sub function. Yeah, and since the A input is in the second stage of the data flow, then you want to make sure that for this input you don't need handshake. You don't want to have a handshake to make sure the A is valid. For example, you start execute these functions that you have the first input to the process one, and then when the data flow to the second stage, you want to make sure the A is still valid because it takes a certain latency to start the process two here. Okay, so you want to make sure the A is valid. Okay, also if it's output, the A is the output. If A is written by the process two, then you need to make sure the memory location you are writing to will not be read before their definition. That means if it's the output, you want to make sure the next process does not read before it's written. Okay, so they all depend on that's the block and block synchronization issue. And using the stable array that tell the AAHLS compiler that there is no need for the synchronization on the A port. Because if you insert the synchronization operation between these two blocks, then the data flow is hardly to execute the data flow. Yeah. So that's that's why the pragma stable introduced. So simply tell the AAHLS compiler that you don't need the synchronization on A. And my design guarantee the A will not be rewritten before it's used. It will be stable there. And it will not be pre-read before I write to it. Okay. Yeah, so use the stable array. Yeah. That's simply because the structure of this data flow in this way. If you have A and B comes in like this, then there's no problem. Yeah, the problem is you skip one data flow stage. Yeah, so make things complicated. Yeah. For this, you just need one synchronization here, then stop running. Yeah. And there's a timing lag between these two. Okay. And this one, in last week, we explained the I/O, the kernel I/O. I repeatedly emphasize for data flow, you use the AP control none, using the AP control none, because you don't need the block level protocol. Okay, the kernel function start SQ if the data is available. Yeah, so you don't need additional block level protocol. So you use the AP control now. Okay, so all processes executed or stored based on the availability of the data. Okay, no synchronization on the block level. Yeah. Okay. Let's look at this. Let's say there's a question. Okay, let's look at this one. So for the data flow design, it seems very simple, yeah. But the complication comes from how you design the FIFO steps. That's a critical thing. Because each data flow stage, first, they may have a different throughput, and they may have a different latency on each data flow stage. And for these two things, you need to clever FIFO design to bridge the difference. Okay, and things can be very, very complicated. If you have a very complicated data flow graph, you can imagine, and they all have a dependency. Yeah, and you want to design the appropriate data FIFO without too conservative. You can always put a very big FIFO and solve everything. Yeah, but it's take too much resource. You want to use a minimum FIFO and keep these things working. Yeah. So that's a very critical in the data flow design. Yeah. And I simply take a very simple example. This one. This one is really, really simple. Okay. And so that's why I'm glad to see the VTIS 2020.2. They start offer a lot of data FIFO analysis tool inside the VTIS tool. Yeah. Because when you run the cosine, for complicated data flow graph, easily get deadlock. Yeah. And how do you handle the deadlock? So one thing you can do is okay, first, the experience is first you create very large FIFO among all the channels and make sure it runs. Okay, and then you try to reduce the FIFO depth, reduce to certain stage. You find out the system can. Okay, then you try to analyze the FIFO. So I remember in the VTIS tool, when you run the cosine, and you can turn on the mode, it will record the FIFO depth, dynamic FIFO depth. And then after simulation, you can read the report. You will see how much data FIFO used in each channel. Okay, and then you analyze, and then you say, oh, okay, I can reduce the FIFO depth. Yeah, that's one way to do it. Yeah. Another thing is if a distance has a loopback, then I said you create very large FIFO and make sure it runs, and then you reduce the FIFO, reduce to a certain point, and the system can. And then you goes in, try to adjust which FIFO create the deadlock. Yeah. Okay, let's look at this simple example here. Okay. So in here, there's a duplicate function, and then it goes to two Gaussian blur functions, and then they remerge to the absolute difference function. Okay, however, these two paths has a different latency. For this blur one, you work on the kernel 5 by 5. For this one, blur 0, you work on the kernel 3 by 3. Okay, so normally a kernel with n by n take n line of a latency. That means 5 by 5, this kernel take a longer latency. Okay, and this bottom path is 3 by 3 is shorter. So for this two FIFO, the FIFO from here and the FIFO here, okay. So which one you need larger FIFO? Upper one or bottom one? 5 by 5 or 3 by 3? Which one need larger FIFO depth? Can anyone answer? Oh, Tony said bottom. Oh, okay. Yeah, because 3 by 3 take a shorter latency. And this thing cannot stop until the 5 by 5 produce the data, right? Yeah. And this one, bottom one, take a shorter latency, so you need to buffer it. Because this thing cannot read until wait for the upper one. So you need a place to save it. Yeah. So if you don't allocate at least 2 lines of buffers, you will see this thing get overflow. Data get lost. Yeah. So this is a very simple example to simply tell you that in the data flow design, the FIFO is the key design aspect. Yeah. Okay. Oh, I thought that's the last slide. Okay. String. The next one is I probably quickly go over. The string for data flow. Okay. That's a Xilinx provide a template library function that's HLS string. Yeah. And this string, the usage is you can create this string with a type. The type could be any C++ native data type, or HLS arbitrary precision data type, or you can have a structure type. Okay, and the depth specified the FIFO. Yeah. And the depth here is simply for co-simulation vocation. It does not specify actual, it does not create the actual FIFO. The actual FIFO is defined by the pragma. Okay, in the pragma, then you set the FIFO depth. And in here, that's only for simulation purpose. Okay, so also provide the API. You can create an instance. You use this way to create the FIFO channel. And then you can do the blocker read and write. Okay, write you can use this way or use this overload operator to write. And for read, you can use this one or use the return value. Okay, and there's a non-blocking. Non-blocking rewrite is very important. Often, when the channel you have a sequence of channel access read, okay? Then if this channel is empty, you don't want to block here. You hope the process can still proceed. In this case, you use a non-blocking read, right? So basically, you use this API with underscore MB, yeah. Or you can first test is full or empty before you actually access the string. Okay, so it provides those API. Okay, in here, when you do the C modeling, C simulation, or C RTL co-sim, that when you do the C simulation, the string channel It's actually is an infinite queue, so you don't need to specify depth. Okay. However, when you do the code simulation, that you want to make sure the depth is sufficient to hold the whole test bench data. Yeah, that's in my last lecture. I also mentioned that you have a cosine. Cosine, you have the C code to generate the test bench. Okay, and then you have a RTL code. This one run the simulator. Okay, so you want to make sure the stream depth can hold the test bench data. Oh. Otherwise, the cosine may hang. Yeah, yeah. This thing, yeah, I think most of you know. Okay, so that's conclude the data flow. Yeah, I didn't address much about the FIFO depth, the FIFO design. Yeah, that's when you actually doing the actual design, yeah, you will experience that it's hard to teach. Yeah, that.